This is Mike Bradley, Marketing Manager for the FTIR products at Thermo Fisher Scientific. In this short presentation, I want to introduce you to how an FTIR works and why you would want to use it. At the heart of the FTIR is the Michelson Interferometer, sometimes referred to as a modulator. To the right you see the infrared source, and the beam goes from there onto a beam splitter, which does exactly what its name implies. It splits the beam. Part of that beam goes to a fixed mirror, part to a moving mirror. The beams are then reflected off of those mirrors back to the beam splitter, where they recombine and then go to a detector. There are many different configurations of this and engineering solutions for how to make this work, but at their heart they're all similar. There is something that changes the path length of one of the beams or one of the arms, here shown as the moving mirror. There is a beam splitter and there is a detector. The key to understanding this Michelson interferometer is this idea of interference. Remember, in my drawing, one mirror moves and one doesn't. So when the two beams recombine at the beam splitter, they will interfere, and that interference is going to change because the moving mirror, as it shifts away, the light has to go farther, so there's going to be a phase shift. In the plot you see on top is the moving mirror in red, and then the fixed mirror in blue. The fixed mirror will never change. The moving mirror is going to start shifting as I click. And you see the effect on the detector signal. As that moving mirror changes, the detector signal gradually drops, and finally goes flat. The result, if I was just to plot the detector signal versus time, would be the interference caused by those two beams recombining at the detector. In the FTIR, the situation is more complex because you have all the frequencies at once. And when this happens, as the mirror moves, you get something called an interferogram, shown there in the center. The large spot in the middle is called the center burst, or the zero crossing. That is the point at which the length of the two arms towards the fixed mirror and the moving mirror are the same, and all the beams would be in phase. As the mirror moves, some are in phase, some are out of phase, so you get this complicated pattern. And you see there, detector signal on the one axis, data points on the other, which is mirror position, which is also time, because the mirror is moving at a steady rate in most FTIR experiments. The Fourier transform of this is what's called the single beam, and that's shown there. That's the response of the instrument, the detector, the mirrors, the coatings, everything in the instrument. Here is a cartoon showing how the components of the Michelson Interferometer are arranged in a typical FTIR. In this case, the Thermo Scientific Nicolea IS-10 FTIR spectrometer. You see there the interferometer, that's that gold cylindrical tube that contains the moving mirror and the beam splitter. The source is shown there, and the beam passes into the interferometer, undergoes modulation, passes through the sample compartment where the sample would be located, and then hits the detector. The laser is used to give a reference frequency for the Fourier transform. Very simple, very clean instrument. Only one moving part, and that's the moving mirror inside the interferometer. And this is how your raw data is converted to a final spectrum. At the top, you see the interferogram due to the instrument with no sample present, and at the bottom is the interferogram with the sample present. If we Fourier transform both of those, we see this single beam due to the instrument at the top, and at the bottom the single beam with the sample present. The additional peaks that you see are due to the fact that those frequencies are missing. They have been removed because the sample absorbed them, and therefore they show as peaks. If we then form the ratio of those two, we get the spectrum in the format that you're used to seeing it. Now, most of the time all of these steps will occur in the background. You won't even see them. You don't need to see them. The only result that you really need is just the final spectrum, and that most of the time is what will be presented. And the rest is up to the physics. Molecules and the vibrations within them will absorb at specific frequencies. If the molecules are chemically similar one to another, they will absorb at similar frequencies. And in the FTIR, the unit which is used to describe this is the wave number, centimeter to the -1. Esters tend to absorb around 1750 wave numbers, carbonyl 1600, hydrocarbons around 3000. Once you've built up a library or a correlation chart of these things, you can begin to extract information now from the infrared. Things such as identifying the molecule or groups within the molecule like carbonyls, or actually identify the molecule itself. You can do quantitation by calibrating the system. The peak heights are proportional to the concentration of material present. And you can do kinetics, where something is changing, you can follow that change over time. There's also a wide range of other experiments that you can do with the FTIR. So why use FTIR? First of all, selectivity. As I mentioned earlier, the molecules absorb at well-defined frequencies. Different molecules absorb at different frequencies, so the spectra are slightly different or very different so that you can identify the materials. You can sample very quickly on an FTIR. You can go from having an unknown to having a final identity in less than a minute when using an ATR, a sampling device we will discuss in a later seminar. The sensitivity, how low can you go? That depends very much upon what you're looking for and in what matrix it is. It's a very common question I get asked, and it really depends upon what you're looking for and what it's in. In one case, I was able to go down to parts per million. That was biodiesel in diesel fuel because there was a peak that stood out alone. Other cases are more complex. The reliability, these instruments can be running for many, many years. There's only one moving part, and that's the interferometer mirror. The cost per analysis can be quite low because the initial investment and the long-term operating costs are not that high. And the skills are very easy to develop. To operate this in a QA/QC lab can be taught in less than an hour. More complex analyses obviously would require longer learning curves, but nevertheless, the basic skills to operate this are very easy to learn. So I hope you've enjoyed and learned something from this short presentation. There's a lot more information available to you here on the web page, so please visit us often. And thank you very much for listening. Have a great day.